Okay, for part 2, we'll talk about the basic procedure for hypothesis testing, and we'll go through one example as well. So let's talk about setting up the null and alternative hypothesis. And I'm phrasing these we're going to do several different examples of hypothesis testing here, some of which we'll explore further in next week. So the null hypothesis is always going to be an equality involving a population parameter. In other words, it's always going to have an equal to sign component, and it's just the default state. The alternative hypothesis is always going to be a strict inequality. By strict inequality, I mean it's going to have a not equal to sign, a greater than sign, or a less than sign. It's going to be one of these three symbols. And again, it's going to involve the population parameter. So suppose that we want to test if the average speed on a highway is more than 75 miles an hour. All right, so what we're really saying here is the average speed, well, again, we're talking about a population parameter here, so we must be talking about mu, because mu is the population average. We're saying it must be more than or greater than 75. So would this be HO or HA? What do you think? Well, since the alternative hypothesis always has a strict inequality, this must be HA, and then HO must be that mu is equal to 75, because that must be the default state we're trying to disprove. So again, mu greater than 75. All right, let's talk about different types of tests. In the previous example, we reject HO in favor of HA if our sample mean is substantially above 75. In other words, if we look at a sample and the average speed of that sample was something like 150 miles an hour, then clearly the average speed is more than 75. But how far away is far away enough? Since we're looking for a number that's above 75, we're looking for some value to the right of 75 in our sample in order to disprove HO and prove HA. So we call this a right-tailed test because we're looking for a number above 75 to support HA. So just to reiterate here, the tail of a test is going to be exclusively determined by whatever HA is, since HA is what we're trying to support. Okay, let's just do some more examples here. Suppose we want to test a claim that the standard deviation of the weights of cereal boxes that come off an assembly line is less than 0.5 ounces. So we're talking about the population standard deviation here, because remember with hypothesis testing we're always talking about a population parameter. So this must be sigma, and we want to test to see if sigma is less than 0.5. So since it's a strict inequality, HA is going to be sigma less than 0.5, and HO is again always an equal to sign, so it's going to be sigma equals 0.5. Okay, what kind of test is this? Is this a right-tailed test, left-tailed test, or it could even be a two-tailed test? What do you think? Correct, it's going to be a left-tailed test because of the less than sign. We're looking for a sigma value below 0.5 or to the left of 0.5. Okay, let's do one more. Suppose we want to test the claim that 60% of students at a particular university own a car. So we're talking about some percentage that we're interested in here. So that seems like that would be P. Remember P from confidence intervals when we talked about those? So our claim is that P is equal to 60%, or 0.6. And the reason why I'm saying equals is because we're saying that 60% of students, that the proportion is 60%. That's what we're looking for here. So that looks like HO. So what's being described here is P is equal to 0.6. Our proportion of students at the university that own a car is 60%. So what would HA be in this case? Well, since we're saying that we want to test this claim that the proportion is equal to 0.6, then we must say that the alternative would have to then just be not equal to 0.6. So in other words, we're testing both the right and the left at the same time. Because if we found a number like 10% or 90% of students owning a car, that would still contradict that null hypothesis, or that original claim. So therefore, it's going to be a two-tailed test. So whenever you see the not equal to sign, it's going to be a two-tailed test. Okay, let's do more. So here's the basic idea. We will reject HO in favor of HA if our sample statistic supports HA enough. How much of enough really depends on our choice of alpha. It's essentially, again, our willingness to be wrong. The proportion of times that we'll reject HO or reject the null hypothesis when it is actually true. So suppose we want to test the hypothesis that the true mean is greater than some number. I like to call this number mu subscript naught, or mu subscript 0, just to indicate this is some number associated with HO, or HA in this example. So we're saying mu is greater than some number, like 75. Okay, so what we're going to do is we're going to draw a sampling distribution. Remember, if we have a large sample, we know the sampling distribution is going to be normal. And I'm drawing this distribution as if HO is true. Well, if HA's mu is greater than mu naught, HO would have to be mu is equal to some mu naught value. So I'm going to draw, here's my sampling distribution of x bar, and mu naught's going to be in the middle. Again, we're drawing this as if HO is true. So we're going to reject the null hypothesis in favor of the alternative if we find some sample average up here, after some cutoff value. And this cutoff value is going to be determined by alpha being just this area right here. Because if this, like, for example, if we pick an alpha value of like 1%, this area would be 1%. It's the probability that we're going to be in this, what's called the rejection region, if in fact this is our distribution we're dealing with. In other words, HO is true. So that's what's called our rejection region. So you want to establish some line and have some rejection region. Even though I wrote a question mark here, I don't actually care about what this value is, because instead I'll just use my z values instead. So I'm going to create some z's, and remember the center of the z distribution, the standard normal distribution, 0, and I just need to figure out what this number is, which we can call z subscript alpha. Or if it's a two-tailed test, we can call it z subscript alpha over 2. All right, this z alpha value is, the name of it is called the critical value. It's just, again, the value that's our cutoff value that's establishing our rejection region. So we're going to reject HO if our sample average falls in this region, and we're going to fail to reject HO if it falls anywhere else. Okay, let's talk about the test statistic. Our test statistic is the z-score of our sample mean. So this is what we're going to be using to compare to see if it falls in our rejection region or not. And the test statistic comes from our data. And if our test statistic falls in the rejection region, we'll reject HO. In other words, there's sufficient evidence to support HA, the alternative hypothesis. If the test statistic does not fall in the rejection region, then we fail to reject HO. And I should have wrote here, and there is insufficient evidence of HA. Let me actually write that right now. There should be insufficient. Sorry about the typo. Insufficient evidence of HA. Okay, so performing a hypothesis test with rejection regions. Let's just do an example. So let's continue our example with highway speeds. Suppose we want to test that the true average speed on the highway is more than 75 miles per hour, and we want to test this as an alpha value of 5%, or 0.05. Okay, so we observe a random 100 cars to test this claim, and find the average speed of those 100 cars to be 78.1 miles per hour, with a standard deviation of 12.4. So 78.1 is above 75, so that seems to support HA, but is it far away enough to disprove that the average speed is in fact 75? So let's test it. So first, we're going to set up the null and alternative hypothesis, which we did before. And again, it's a right-tailed test. The alternative hypothesis is that mu is greater than 75, and the null, being the default state, is that the true mean is equal to 75. So for step 2, let's draw and set up our rejection region. Just to walk you through, our third step is going to be to calculate the test statistic to see if it falls inside the rejection region or not. And then our fourth step is going to be to make the conclusion. Do we reject HO or do we fail to reject HO? Okay, so let's do this. So here's our curve. Again, this is our sampling distribution of x bar. Just like before, the average is 75. We don't know what that number is. We want to test at 0.05, so the blue area is just going to be 0.05. And that's setting up our rejection region. We need to look at Z's. So our first step is going to really be, let's find the Z value. Let's find this critical value here to set up our rejection region properly. So let's do that. Okay, so we have to find Z alpha. There's a lot of choices as far as how you can do this. You can use the Z table backwards. In other words, we know the area here is 0.05. That means this area must be 0.45. We can use the table backwards to figure out what this number was. We can use the last line of the T table and just look up, T of 0.05. Or we can actually use, sorry, a table in your text, table 6.2. Oh, sorry, I thought that was 1 second. 1 moment. Let me show you what the table looks like. There it is. All right, so here's what table 2 looks like in your book. Table 2 gives you some common alpha values, and then they tell you exactly how to break it down, how you're going to set up your test. Since we're doing upper-tailed or a right-tailed test, and we have an alpha of 0.05, our Z value, or critical value, is going to be 1.645. So that's the number we need. Okay, let's go back. All right, so I'm going to do that, and I get 1.645 for my Z alpha, my critical value. I'm going to reject HO if our test statistic falls to the right, falls in that rejection region, and I'm going to fail to reject if it falls to the left. Next, let's calculate the standardized test statistic. Really, we just need to find the Z-score of our sample average. Remember, our sample average was 78.1. Right, our sample average was 78.1, so we just plug that in. Our mu naught value, our mu under HO is 75. Our sample standard deviation is 12.4. So again, we need to figure out sigma x bar, the standard deviation of this distribution, which remember is just sigma over the square root of n. We don't know sigma, so we'll just use s instead. So it's going to be 12.4 divided by the square root of our sample size, which was 100. So that gives me 3.1 divided by 1.24, which is actually exactly 2.5. So our test statistic is 2.5. 2.5 falls somewhere over here. It's to the right of 1.645, so let's draw a line there. So here's our sample average of 78. The Z value associated with it is 2.5. That clearly falls in our rejection region. So that means that's our conclusion. Our conclusion, oops, I never really wrote it. Our conclusion is just going to be to reject HO since it falls in our rejection region. So this is how you probably should write the answer on the test. Just write reject HO. But technically speaking, we want to include a measure of reliability. We might want to include the words of the problem in there. We can do a little better in practice than just saying to reject HO. Well, one way is we can say support HA, but that really just isn't any better. Because remember, for rejecting HO, that means we're supporting the alternative. Either way, we can phrase this. You should always include your measure of reliability. So one way that we can say this a little more practically is we can say at alpha equals 0.05 or at a 5% significance level, there is sufficient evidence that the true highway speed is more than 75 miles an hour. Or you could say there's sufficient evidence to reject that the average speed is 75 miles an hour. Either way, I always like phrasing things in terms of the alternative. I think it sounds a little better. But this would be one way of practically interpreting it, which is what I'm going to ask you to do for your next project. But again, on the test, if you just said reject HO, you would get full credit. So this is all I'm looking for on the test. Well, okay, I'm trying to circle this, but it's not working. There we go. Okay, and again, here's that table that I referred to. So use this table. It'll help you set up any of the critical values and give you your rules for rejecting.